Hello. I'm going to talk about the development of VRay next, which is the next version of VRay, and which will be released with luck next week. I don't want to just list features, so instead I will be talking about 3 specific stories from the development of VRay next that were kind of interesting for me. The first story is about updating the Embree library to a newer version and wrapping up the integration of Embree in VRay. The second part will be about simplifying the VRay code and making it faster. And the third story will be about the adaptive DOM light. So let's start with the first one. Embree is a library by Intel for fast intersection of rays with all kinds of geometry. Before that, when we originally developed VRay, we had our own intersection code for all the different primitives that we have in VRay, which is triangle meshes, motion blurred meshes, hair, particles, and things like that. So when Embree appeared a few years ago, we started looking into it and trying to see if there's any advantages to using it in VRay. We did some experiments even with some of the VRay 2.4 or 5 version, and it seemed to be actually pretty good. So with VRay 3, we integrated Embree officially as a part of VRay. But we didn't use it for everything back then. The original VRay 3 only used Embree for triangle meshes with or without motion blur, but the motion blur had some limitations, and in certain cases we fall back to our old code. And gradually we added support for more things with Embree, like hair, VRay proxies, instances. All of these were added at various VRay 3 updates. Why we did all this? It's because Embree is generally twice as fast as our own intersectors, which were quite old at that point. The original VRay code used KD trees. It did not use any modern processor instructions. So Embree was a better choice for us and gave us roughly 20% improvement in the total render time. With VRay next, we updated to a new version of Embree. First, because we obviously need to keep things current a little bit. Then it also had some interesting new improvements in the hair intersectors that we wanted to use, and it had the ability to do intersections not only with triangles, but with quadrangles, which we thought was worth exploring. We also, for VRay Next, we also added multi-segmented motion blur. And the plan for during the VRay Next release cycle is to work on reducing memory usage for Embree. When we did the original integration, we did a couple of modifications. The original code, Embree, is open source, so we could just modify it to fit our needs. But for whatever reason, those changes couldn't make it back into the official Embree code, so we had to keep them separate in our own internal code. And I just want to give an example here of the hair intersector that we implemented for Embree. The original one in Embree is fast, but it's good for thin hairs that you don't really notice too much. Like, you don't see the thickness of the hairs very well. So, but we had cases, we had customers that actually wanted to create these thick hairs, and we had to do a better job than what we had with the original Embree code. And especially on this image, if you look closely in the left image, you can see some shadowing artifacts. It generally looks okay, but if you look closely, you start seeing these little problems. And in our code, we wanted to fix all this and get everything nice and correct. So we did all these things, and we used originally Embree 2.3 and everything was fine, but then when we decided to update the code, we realized that it's totally different. Many things had been refactored, and it was better, but it was really not clear how our modifications would go into this new code base. So one of our developers, Martin Krustiv, basically decided to take our modifications and rebase them on top of every single commit in Embree from version 2.3 to 2.13, and fixing any issues that came along the way. Obviously, this was a very long process, very unpleasant. And having unit tests where we could test our modifications and make sure that everything works correctly was super important. But it was done, and it was a process that took a really long time. We started it during the VRay 3 release cycle, but it ended up being ready for VRay next. And these are some images done with our updated Embree library. I would also like to point out that I didn't actually force Martin to do this. He volunteered, so, but I would really like to thank him. I'm really hoping that for the next update of Embree, we won't have to go through the same thing, and hopefully it will go a lot faster, because Embree is at version 3 right now, and it has other interesting features that we want to exploit, so I don't want to spend another year on that. So, the next part of my talk is about making VRay faster, specifically by using more modern SSE instructions. Originally, when I wrote VRay back in 2000, there was SSE instructions were not available, so I didn't even know how to make the code that much future-proof. So for the longest time, and during the VRay 3 release cycle, we just used plain vectors and colors, like 3-component structures for everything. And of course, modern CPUs now can do this much more efficiently. And the question was, however, because we have a huge code base, let's go to the next slide. Yeah, it has like more than 3,000 C++ files, header files are more than 5,000, and actually counted how many lines of code contain vectors, and you see that it's 50,000. So how do you make a change like this? Well, the first thing that I had to do was obviously to be sure that this change would actually be useful, like it will actually make our code faster. So during the VRay 3 releases, I think in VRay 3.6, I actually implemented some little pieces of code with SIMD structures, like the VRay material. And it did show measurable improvements in performance. So that's why I knew that doing it for everything would probably make sense. So the VRay code is structured like this. We have a bunch of utility libraries for intersecting rays with various types of geometry, texture management, stuff that doesn't really require a renderer, but which a renderer can use to do its actual job. Then we have the actual VRay core, containing all the rendering algorithms. And then we have the various plugins, the various integrations of VRay for 3ds Max, VRay for Maya, and the command line version of VRay. And then on top of that, we have all the various plugins that extend those, like materials, lights, texture maps, and so on. So making this change, it's a fundamental change in all these pieces of code, was going to be really, really complicated. And on top of that, it's not like a simple find and replace operation. You can't really just turn everything into SIMD structures because they are a little bit larger. So every SIMD vector requires 16 bytes, whereas if it's just regular 3 components, it will be 12 bytes. It's not a big difference, but if you have large arrays of colors or vectors, it does make a difference. And also, working with such structures has some limitations on the alignment of those, like where they are in memory. The vectors and the colors need to be precisely aligned at 16 bytes, which is not possible to do in every single piece of code. Also, some of the calculations were not really in any way performance critical, so there was really no need to go and change everything. And I was wondering how exactly to do that. There's a quote by a book, The Mythical ManMonth. It was originally about flowcharts and other things, but it's also valid for code. And basically the idea is that you start with your data structures and then the code follows from that. I haven't actually read the book. For the longest time I thought it was called The Mythical ManMonth, and I thought that it's some kind of science fiction book. So now I know better. So there are a few key structures that are useful for VRay, like rays and intersection data and the VRay context that's used in shading. And my idea was to basically just change those specific structures first and propagate all the changes through the rest of the code. Of course, we made sure, and here Martin Kristof also helped me, we made sure that the SIMD versions of all the vectors and colors and matrices had the exact same interface as the non-SIMD versions. So usually I would just have to change the type of a variable or a method argument, and it would all hopefully work automatically. So a change would look like as innocent as this. You just change 5 lines of code, converting some structure member from a vector to a SIMD version of this vector, and then you break everything and nothing compiles. So I was wondering, I tried this. So you change those 5 lines, nothing compiles, you get thousands and thousands of errors, and how do you fix that? And originally, I thought that I would be able to do this in a branch, do all the modifications, make sure that the code works, and then merge it back. But, and I actually started doing this, but it turned out to be really complicated because, of course, I was doing these changes, but the other guys were also working on the code, so I would do some modifications, things will work, then I will take the latest changes from the master branch into my developer branch, try to compile, and of course things would break, and I just realized that it's not going to be a very good strategy to continue working in this way. And on top of that, we have some projects like Phoenix that still needed to be able to compile with both versions of VRay, both the old one, VRay 3, and VRay Next, using the new SIMD classes. And I hadn't originally thought about this. So what I ended up doing is basically have a compile time switch that allowed me to switch the entire code from the original non-SIMD versions of the structures to a SIMD version. And then I would work, so this is kind of what it would look like. Up on in the first half of the screen is the SIMD version of some internal structures used by VRay, and then you can switch to the lower part, which uses the non-SIMD versions. And my workflow would be like this: create a new branch in Git, switch everything to, or whatever I was working on, to SIMD types, try to compile, fix a little bit of issues, for example, in a few CPP files or in one single module of VRay, like a plugin or a texture, then revert back to non-SIMD types, make sure that things still continue to compile, and then merge these changes into the master branch. And I made sure that whenever I tried to do something stupid, the compiler would tell me, so I would get a compiler because of it. So that meant no implicit type conversions. I had specific functions to convert from SIMD to non-SIMD types and back. And then I had all these really little branches where I would, and you can see at the top of the screen, where I would do a branch, make some modifications, and then merge it back. And then at some point when I thought that everything would work, I would just change to define in the master branch, and everything compiled with the new SIMD versions. And that actually worked. I was really surprised. Of course, there were some really minor bugs that we had to fix, and they showed up a few weeks later. But mostly it was relatively very, very tedious and very long, but relatively painless process. And we ended up with 3 kind of type defs that can map to either a SIMD or a non-SIMD version of some type. There's a float3 type that we use for our intersection code. There's a shade vector that we use in VRay as part of the ray context. And then there is a shade color. And there are other things as well, but these are the main types. And I had to go through the entire VRay code base several times, once for the float3, once for the shade vec, and once for the shade color. Most of the files were affected in this thing, but the result is worth it. In some cases, we have up to 25% faster rendering, and as a bonus point, we got a header that we can use to switch between the previous version of VRay and the new version of VRay, and we use this in Phoenix to be able to compile for both versions. Overall, took about 2 months. And like I said, I didn't do everything in SIMD. Some things just didn't make sense, but most of the calculations now for shading and for rendering work with SIMD types. So that story had a happy ending. The next story is about the adaptive dome light in VRay, which is a new feature for VRay Next. It's basically a continuation of so we did the adaptive lights algorithm for VRay 3.5. It worked surprisingly well for our GPU renderer, but also for VRay CPU. And we wanted to use the same idea to optimize other calculations in VRay, in this case, the dome light. And it's a really simple idea. You try to figure out which parts of the dome light affect which parts of the image, and you try to optimize the sampling for that. Sen Atanasov is the developer who worked on this, and he will talk about this in more detail at Total Chaos, and we also have submitted a talk at SIGGRAPH this year in Vancouver, and we're going to present that as well. And something else that occurred to me after that, this technique was only possible because we had worked on having a good adaptive image sampling algorithm for VRay, which we added in VRay 3.3, I think, the variance-based image sampling. And I just want to show how this works. So here we have some image done with the adaptive dome light. And if you look closely, you can see that we have parts of the image that have different noise levels if you use fixed sampling, just because it samples the 2 parts of the image in slightly different ways. And if you look at the VRay noise level render element, you can see that there's a line where above you have more noise and below it you have less noise. And we need the VRay adaptive sampler to sort of even this out so that in the final image you don't see that there's any difference in the noise levels between the 2 parts. This was really important. Without having the variance-based adaptive image sampler, we wouldn't be able to use the adaptive dome light in this specific way. So Sen started working on this last year. He did some work and some experiments, and he couldn't, for some reason, get any good results. Like they were either slower, and it was very discouraging. He, at some point, just came to me and said, that's it. I can't make this work any better than what we have right now. And this was weird for me because I couldn't imagine a universe where this algorithm would work slower than what we had before. So I looked at what was happening there, and I noticed that Sen was using a structure that we wrote for the adaptive lights algorithm. It's called a light grid. And anyway, it has a method that does something and returns the probability for selecting a light source or a part of the dome light, and this is what the code read, and this is what the comment said. But what it should have said was this. It did actually calculate not the probability, but the inverse probability. And Asen didn't know this, because he had no reason to doubt the code. I had written it, and Vlado never makes mistakes, even though the VRay changelog is full of mistakes that I've made. But anyway, that was one of the problems. He didn't realize because the actual calculation was buried in a few other methods of this class, so he didn't realize that it was actually the inverse probability. And once they fixed that and a few other things, the code magically worked. And on my test scene, it was about twice as fast as our own code for the same noise level. So we were happy. We released this new algorithm as an option in the VRay Dome Light in VRay Next, the first beta version. And we, or at least me, thought that it's a job well done until there's this forum post by some of our beta tester. And he says, well, guys, this is all fine and everything. It's really faster, but I get some artifacts in my image which look like this. If you look carefully or at the cupboards on the screen, you could see some blocky artifacts, or on the windowsill before the window, you could also see some kind of patches of different light intensity. And this basically made the image totally unusable. So we got the scene from the customer, and I tried to figure out what's wrong, and I found out what's wrong, and I realized that we may have to give the whole thing up. To explain why, I will take a step back and explain what's multiple important sampling. It's basically a method to combine several different sampling strategies in ray tracing. Basically, you have two ways to calculate the same method. One is based on the light source, and the other one is based on the material. And in some situations, one method is better than the other, and there is a particular way to combine both results so that you get the least amount of noise in the image. So it's kind of like a puzzle where you have two pieces and they have to fit together to get you the whole result. Here on the left side, we have our own original dome light. And on the right side, we have the adaptive dome light. And you can see that it does have some blocky artifacts in the two different strategies. But when you add them together, they completely fit and they form the correct image. And it renders a lot faster. Even though just looking at the intermediate results, you might think that it's not really usable. When you add everything together, it matches and it works fine. So this is in theory, but you can break this sort of balance in many, many different ways in user scenes for different reasons. And I've listed some of the reasons, but the most, so one common reason was different highlight and reflection glossiness. We have this option in the VRay material where you can use different values for this parameter, and it turned out this is a problem because it breaks the balance between those strategies. And we disabled this in VRay Next, so now you get a warning and this doesn't work anymore, so you only use the reflection glossiness. And also, if you have objects that have different visibility to different types of rays, this also breaks the balance. For example, if an object is not casting shadows, it will modify the result that is computed by the light, whereas the material result, the BRDF result, would still stay the same, but they won't add up to the right thing. Of course, this was kind of an issue also when we didn't have the adaptive dome lights, but at least you didn't get artifacts in the image. You got some result, which was, you could call it accurate, and it didn't cause any apparent problems. But when we switched to the adaptive dome light, this was very, very obvious. So in this particular scene that the user gave us, the problem was that he had an object that is visible to reflections into the camera, but does not cast shadows. So shadow rays would just pass through this object without doing anything, but reflection rays would stop and not be able to find the light. And this is obviously not physically accurate, but it turned out that this particular situation is very, very common in the world of architectural visualization. Why? This is why, for example, you do an interior scene, this is an motion scene, you've set up the lighting correctly, you've chosen the right HDR, it's nice and sunny and everything, but the actual room that you're rendering is not on top of a mountain, it's maybe someplace else, and you want to use a different you want to see a different environment through the windows. So, for example, you can use this spherical panorama taken with my phone in the middle of nowhere. You can see Mishu Jurev, the team lead of VRay for Maya, taking a picture of something over on the right side. But imagine that we want to use that as background for our image. So the way people usually do it is they put some type of geometry. It could be planes, or it could be, in this case, a cylinder that wraps the scene, and you map this cylinder with material that just has a self-illumination map. It doesn't have any diffuse component, reflection, or anything. It just is there to show the environment. So the map is actually attached just to the self-illumination slot. And if you just do this and render, you will get some result. You will be able to see the background. And it will reflect and everything. But of course, the lighting now is not correct because this object is casting shadows on the rest of the scene and blocking the sunlight. So what you could do, obviously you can make this object only visible to camera rays so that you still get the background, you still get the right lighting, but the reflections look weird because they still reflect the original dome light in the HDR. And the way to fix this is to make this environment object not casting any shadows, but visible to reflections, refractions, and visible to the camera. And these are the properties that you would use in 3ds Max to do that. And this is the result that you want. So if you flip back and forth between the original image just lit with HDR and the one with the mapped environment, you can see that the lighting stays the same, so we still get the result that we wanted originally. It's just the background is different and it's correctly reflected in all the other objects in the scene. But as I showed, this type of thing caused issues for the adaptive dome light and caused these ugly artifacts. And I didn't know how to fix this at all. I had no idea. One of the things that we could do is just put a warning up for the user and do nothing, and we would still get artifacts, and you would have to explain to users that they have to do something about it. We could automatically turn off the adaptive dome light if we detect such cases, but then we lose all the performance improvements that we did. And it would basically make the algorithm only applicable in a very small number of situations. We could just not use it at all or do something else, which I had no idea what that was. We kind of did eventually find some kind of solution for beta 3 of VRay. The only thing that I could figure out was basically to detect whenever a ray goes through such weird object that is visible to some kind of rays but not visible to others, and change the sampling strategy and the weights for the multiple importance sampling in a way that would not cause any artifacts. And this worked, but I realized that it will be very difficult to do this on the GPU. It was easier in the regular VRay code because we first trace a shadow ray and we know whether it passes through any such objects, and then we can modify the probability that we pass to the BRDF to calculate the lighting and the way a light reflects from the material. But we could not do this on the GPU. The GPU works the other way. It first calculates the amount of light that would go through the material, and then it traces the shadow rays. So at the point where I needed to compute the probabilities, I didn't know whether the ray will hit any such weird object or not. Also, it caused occasional fireflies, and this non-optimal sampling strategy was actually, in some cases, quite slow to render. And the final result that goes in VRay next actually occurred to me just last Friday, literally last Friday, when there was no time and we had to make the branch for the new release, and I had to figure something out. And what I decided eventually to do was basically just remove the specular contribution of the lights for any such weird ways and replace it with that of the environment geometry. And this works for VRay, but it requires that, of course, the renderer can distinguish between diffuse and specular reflections and lighting. And some renderers do that, but others do not, and it's more difficult to fix the problem in that case. So this is the original scene that with the artifacts. It's not the actual user scene. That's something made by our 3D guys that I broke on purpose, but it was a similar situation. And then this is the fixed version. And if you compare this fixed version to just lighting with regular dome light, the lighting is exactly the same, and the reflections are correctly replaced, and we get no artifacts at all. There is also a view of the sampling rate render element, just to show that the adaptive dome light actually manages to sample the image a lot less, and it gives you the same amount of noise in quite a bit shorter render time. So even though the sampling rate looks weird and it has these blocky artifacts in it, it still renders and looks totally fine. And this only works because we have the adaptive sampler in the first place. And so one problem for me was why it took so long to find a solution for this is because there are no papers on this. Like usually papers deal with physically accurate stuff where everything matches and the math is correct. But there's not a lot of research done on these non-physical situations. And there was nothing that I could just go in and read about this. So then the next thing was that I could do was basically figure out how different renderers deal with this situation. It's kind of part of my job to play with different renderers and to know how they work and which are the strong points and which are the weak points and where VRay is in all of this. So it was kind of a useful excuse to play with different renderers. And what I found out and what I realized is that renderers generally deal with direct illumination in two slightly different ways, which I called PBRT style and mixed style. And it's a fundamental difference between renderers. Even though two renderers can be brute force, they can give you the same result, the way that they get there is completely different. And this leads to differences in how they deal with such non-physical situations. If you don't know what PBRT is, it's a renderer it's an open source renderer that comes with a book called Physically Based Rendering. It's been around for a while, but sadly not when VRay was first created, so I didn't read it. But nowadays when people say that something in CG is done by the book, they mean this book. So what PBRT does, basically when it evaluates lights, first it generates rays for the light, then it generates rays for the material, and it traces all of these as shadow rays, and then after that it generates actual rays for sampling, reflections, GI, and so on. And here's a graph on how this might work. Basically, from each hit point, you get shadow rays generated by the light, and you get another set of shadow rays generated by the material. You trace them with their shadow ray set, flag set. And then after all this is complete, you generate rays for reflections or GI or whatever. And the other way to do things is to split the calculation of direct illumination basically in two parts. When you evaluate lighting, you just do one part that works with shadow rays, and they are generated by the lights. And then when you normally trace reflection rays or GA rays from the material, if such a ray happens to hit a light source, then you compute the other half of the direct illumination. And this is just the way it works. You have one shadow ray generated by the light, another reflection ray by the material, and that's it. So the advantages of the PBRT way of doing things is that you don't get problems with objects that cast shadows but are not visible to reflections and vice versa. But the drawback is that you have to trace more rays. And if you work with a renderer that works in this way, it's very easy to generate lots and lots and lots of rays because, and I've tried this, I played with one of the renderers here that spits out ray statistics about the traced rays. And basically every time you add a new light, you would multiply not only the light samples, but also the specular samples and the diffuse samples, and it can get really, really slow. Right. So I also had this very simple experimental picture where I tried to replicate the same way, the same problem in a simpler situation. There's just one dome light that illuminates the scene. There's some reflective object, and there is a plane that is visible to reflections but does not cast any shadows. And as you can see, different things happen with different renderers. The first one at the top left is VRay Next. And it's kind of maybe acceptable, I hope. You get the, so one of the spheres is in the shadow of the plane and the other one is not. For the one that is inside the shadow, the highlight from the sun is blocked and you get the reflection from the so-called environment plane. And the other sphere is just the regular specular highlight. For the next renderer, the one on the top middle, didn't initially do exactly what I wanted. So I had to do was basically to turn off the specular contribution of the dome light. But then that killed all reflections of the dome light, so I had to set the same texture map as an environment map, which just affects reflection rays. So a little bit more complicated setup, but similar result. Then the next renderer also kind of did the right thing, except that it doesn't really distinguish between diffuse and specular contributions from a BRDF. And while it also kind of gives you the correct result, there is this black hole where the highlight would be on the sun. So, and that's, like I said, that's a problem that must be solved in other ways. Then the lower left and middle image is another renderer where I couldn't really get it to do what I wanted. In the first image, you can see that if you just turn off shadow casting from the plane, you get some kind of weird mix in the reflection between the environment and the plane, so the reflection is not quite right. And I still get the highlight in the middle sphere. It's still there. So I tried to fix this like I did with one of the other renders, but I just couldn't figure out the right combination of settings. So maybe if I created another sphere that would have the environment mapped on it, just for the purposes of reflections, maybe that would have worked. But it's more complicated setup. And the last picture here on the bottom right is VRay 3.6, which is, again, maybe kind of works, but you still get the highlight from overlaid on the reflection in the middle of the sphere. And there's also, if you look very carefully, there is something very weird going on with the reflection of the sphere inside the plane. There's some kind of halo-ish thingy there that looks totally weird. So yeah, different renderers deal with this thing in different ways. And because it's not physically accurate, there's no one correct way. So we can't say that this is the way to do it. I hope that what we implemented in VRay would actually be acceptable for users, but we'll find out next week.